to offer access through Instruct. And I have to say that I've really seen firsthand as a student, as a researcher, and in a facility, what an amazing impact Instruct and the community and the wider community has in terms of offering training opportunities, access to equipment, and I think it's a really amazing achievement for the team to bring everybody together here today. So everyone's got their phones down, so I'll move into the talk. Everybody in this room will have heard about the advances recently in cryo electron microscopy, and it was 10 years ago now that Werner Kohlbrand published this review article coining the term the resolution revolution in cryo electron microscopy. Helen Sable, a couple of weeks ago, termed this the Big Bang, which I also quite like. So, we really had a culmination of improvements in hardware and software coming together and really transforming what cryo electron microscopy could do for biological research and for life sciences research. So what has happened in the last 10 years? Well, you'll be pleased to know that more has happened than just the cryos reducing a little bit in height. So the new instruments, the latest cryos microscopes, are a little bit shorter than their predecessors. But in reality, what we've seen is a huge development in terms of both the hardware available, even in the last 10 years, in the hardware available and our transmission electron microscopes, but also the software. So what does this mean in terms of the types of questions that can be tackled? Well, if we take the Glacios transmission electron microscope, for example, this is there are more of these Glacios instruments really than any other dedicated cryo TEM in the world. And if we go back to 2017, we could see that if we take everybody's favourite test specimen, apiferritin, it was taking about 30 hours of data to be able to achieve a resolution of about 3.3 angstroms for this test specimen. If we fast forward to today, taking into account the hardware developments, particularly, I've got to say, advances in detector technology, as well as optical improvements, we can now achieve a resolution which is an improved quality. So we can now get down to sort of like 1.5 angstrom resolution of this test specimen, apiferritin, but in a much shorter time as well. So this one, it was about 8 hours of data acquisition. So even since we termed this coin the resolution revolution, we've seen real further advances improving the data quality and quantity that we can collect. So, of course, hardware is really important in this, but actually, for me, one of the most interesting and impactful things that has happened over the past few years has been the improvement in the software. So, Thermo Fisher, in order to collect single particle electron microscopy data sets, so collecting many micrographs, many images of our sample of interest, Thermo Fisher have this EPU software, which has got to be my favourite example of a marketing exercise, because EPU stands for E pluribus unum. So put your hand up if you recognise that phrase, E pluribus unum. So it's out of many one, which is also the motto of the United States of America. And the idea is we have out of many particles, one structure. Although I've been saying to them we need to rename, because now out of many particles we can get some structures, many structures. Anyway, I think it's quite a fun name. And there's there's been lots of advances in terms of the software side of things. But the thing I really wanted to highlight was that if we take one of our state-of-the-art transmission electron microscopes, one of our Titan Cryos microscopes or our Glacios instruments, you can put 12 grids inside that microscope, 12 grids in your autoloader. And until a few years ago, you would load one sample into the machine, you would set up your experiment, that experiment would come to an end, and then you would repeat and put the new sample in. So when I was running the facility in Leeds, our standard session lengths would be anywhere between 24 and 96 hours. So we put this grid in, collect the data, and then move on to the next one. What multi-grid EPU allows us to do is set up a series of experiments on our entire cassette, press go, and then come back to the microscope to 12 data sets afterwards. And this is enormously powerful because it drastically reduces the amount of operator time, time for somebody, a researcher or facility staff to be sat at the instruments, and is also really flexible. So say, for example, you've got 3 different projects in your microscope. One of them you want to collect, a big data set on, but the other ones it's early stage. You want to just collect some small data sets, process, see what the data looks like. Well, you can do all of that in one session. So rather than spending to collect 12 data sets, really days of time sat at the instrument, you can now do all of this in a couple of hours, which of course frees everybody up to go and do something much more productive or interesting with their time rather than sitting and clicking on a screen. And there's a really nice case study that I think nicely illustrates that. And that's a piece of work that's very recently been published by Basil Grieber's group in collaboration with a team at Thermo Fisher, Abbe Katech's team. And it focuses on this macromolecule CDK7. So CDK7 is really of a lot of interest in terms of drug discovery as a master regulator of cell growth and division. But in terms of a target for structure-based drug design, it's really not the easiest thing to work with. So there are a large number of structural homologs, X-ray crystallography was not yielding any high-quality structures, and finally, even by traditional standards in cryo-electron microscopy, this thing's relatively small, it's 85 kilodaltons. So what Basil and his team were able to do was purify this protein and then make use of the multi-grid EPU and the software advances there to collect multiple small, in this case, 1 hour data sets on CDK7 with the particular molecule of interest. So and in this particular case, they screened, In this particular case, they screened 24 compounds, so it was about 24 hours worth of instrument time. And even with just 1 hour of data on this really quite small and non-ideal specimen, they were able to achieve a resolution of 3.5 to 4.5 angstroms. But even at this, low intermediate resolution, we are able to really nicely, clearly see density for the small molecule. And that then gave them confidence to go away and collect longer data sets, larger data sets on the cryos, and obviously resolve some beautiful electron density of both the protein and also the small molecule of interest. So I think this is a really nice case study because it shows I'm always really reluctant to use the word high throughput because it all depends. Your perspective, your definition of throughput will always depend on where your benchmark is and where you started and where you are now. As somebody who started off doing cryo-electron microscopy with a side entry instrument and collecting data manually in the middle of the night, this feels really high throughput. But obviously, in terms of a wider structural biology context, there are still techniques out there that can provide much higher throughput. But still, I think this is a big step change in terms of where cryo-electron microscopy has come from and a really strong indication of where it's going and how throughput will be improved in the future. So all of these hardware and software improvements have led to more single particle structures being solved than ever before. And I really love this graph. So this is the number of structures released in the PDB by structural technique. So we have cryo-EM in the blue, NMR in yellow, and X-ray crystallography in the dark blue at the top. So we did think that this year, 2024, might have been the year that there were more structures solved by cryo-electron microscopy than any other technique. It's not looking like it's going to happen, so I think it will probably be next year when the curves finally cross over. But it's amazing to see just how widely now this technology is being adopted and just how many structures it's being used to solve. And of course, the majority of these structures that are being solved are of isolated protein complexes. And when we're looking forward now to the next 10 years, the thing which I'm personally really excited about is in situ structural biology and the potential to solve structures in their native environment. So I always like showing these animations from a very talented artist, David Goodsell. Highly recommend if you haven't seen his work to Google. This is an example. Keep doing this. This is an example from it's essentially it's a artistic but scientifically accurate rendering of a neuromuscular junction in this case, and I think it really gives an idea of the molecular crowding that happens inside a cellular environment. And it's a little bit of a range, but a good rule of thumb is that there are probably 2 to 4 million individual proteins in each cubic micron of a eukaryotic cell. So in every single, so we're not just talking about in one cell, we're talking about in 1 cubic micron of each cell. And with cryo-electron microscopy, we have some potential to start looking at these structures, not just in an isolated format, but inside a cellular environment. And I think this is extremely cool. So the predominant way that we're looking to solve structures at the moment is not by using single particle techniques, where we're working with isolated proteins, but by working with cryo-electron tomography. And it's quite interesting, if we look in the PDB trends and see how many structures have been deposited using single particle analysis versus cryo-electron tomography, the curves kind of show a lag of about 6 to 7 years. So if we think about how widely single particle has been adopted, I think we may be, if the trend continues, we'd be looking at 6 to 7 years before cryo-electron tomography had a similar adoption. And historically, people really, and really myself as well, kind of considered cryo-electron microscopy to be a lower resolution technique. And that's why I really like showing this example, again, of apoferritin. It's not a real-life protein, it's a very convenient test specimen. But a data set was collected really just to see if we push the limits in terms of the microscopy and the data processing, what resolution can we achieve. So with 100 tilt series and about 31,000 particles, they were able to achieve a subtomorem averaging structure of 1.5 angstroms of their apoferritin. But of course, this isn't solving structures inside cells, which is of course where we would like to move towards. So, if we want to solve structures inside cells, and we want to use structural biology approaches such as transmission electron microscopy to do that, we've got a problem. And that problem is that cells and tissues are, generally speaking, apart from in a few cases, pretty much too thick for you to directly transmit the electron beams through that specimen. So we need to prepare that sample, we need to thin it somehow before we can put it into the transmission electron microscope. And of course we can work with cells grown on grids. We can also work with tissue, high pressure frozen. But we need to perform a thinning process. And the tool of choice for this is to use a dual beam instrument. This would be a scanning electron microscope with a gallium or a plasma beam, an ion beam, which allows us to mill and ablate our specimen. So Thermo Fisher offers 3 flavours of dual beam, and I'd be happy to talk in detail for anyone who's interested. But I wanted to show you some examples of the kind of data which these instruments can produce. So I wanted to just start off by saying a lot of people think about dual beam and about thinning samples really as almost a sample preparation technique. We're using these instruments to thin specimens. But the SEM, particularly in this Hydra instrument, is in of itself a super impressive instrument. So there is this approach called slice and view, where we can take our cryogenically frozen samples, there'd be no fixation, none of anything else, and we can directly mill away the specimen and then image using the SEM. So I'm a TEM girl, right? But when I saw these images from the SEM, it really blew me away, because what we're looking at here is completely unfixed, and yet we can see all of this amazing molecular architecture, the membranes, the thylakoid stacks, the mitochondria, the Golgi, really in astonishing detail. But of course, what mostly we're using this technology to do is to take our sample and mill a lamella, which we can then put into the transmission electron microscope. So here is an example of an animation of milling an ice cube by the looks of it. But we can then take this thin lamella, and here's some examples generated in the Arctis instrument, and we can then put those into the transmission electron microscope. And that allows us to generate data and then subsequent subtomogram average structures of our specimen of interest, such as this ribosome, to potentially very biologically informative resolutions. So this ribosome structure here, which was solved in its native environment inside the cell, is at 6.5 angstroms from just 6 tomograms on these lamella. So I think it's a potentially really impressive approach. And of course, So we're seeing cryo-electron tomography. We're seeing more and more interest in this, and I think it's been fascinating to hear some of the talks this morning. I think in Tassos's talk particularly, he spoke about the power of AI in generating structures, but I think the thing that strikes me during some of these talks, and also during an AI workshop we had last week, is the number of times when AI doesn't give us the complete answer. So I guess the thought that I want to leave you on is maybe we can use solving structures inside a native environment. If we do this enough, if we solve enough of these structures in an in-situ environment, maybe that will give us better data to use these machine learning and AI approaches on. So I've really not had a chance to talk about all of the different cool things happening in electron microscopy at the moment. So if you do have any, if you want to come and have a chat, please do. I'm also joined by my colleagues Javier and Florence. So please come and find them at lunch, coffee, the bar or the beach later. Okay, and that's everything. Thank you very much.